Now in this chapter we will be talking about self-inductance. Now the particular logic behind self-inductance is that it is also possible that the EMF which is induced in a single isolated coil due to a change in flux. Say suppose this is a single isolated coil, this is my coil. Now if you pass current, the EMF that generates a magnetic field. Now, if you change the current, there will be a change in field. Now, because of the change in magnetic field, you will have an induced EMF which tries to stop this change in magnetic field. So, this isolated coil, in a way, due to the change of flux through the coil by means of varying the current through the same coil. Now, this particular phenomena is called self-induction. This is called self-induction. That is, it is inducing itself. Now we know let the number of turns be n. So the change in flux be, say, Ib. Therefore, we know n pi b is directly proportional to I, which is n pi b is equal to L into I. And this particular L is known as your self-induction proportionality constant. Proportionality constant. So this is what we can understand. So now when a flux linked with a coil also changes, an EMF is induced in the coil. So that particular induced EMF can be expressed as minus d upon n pi b into dt, which is nothing but, if you put this value, that is L minus L di upon dt, the change in current, that is a change in current, and this is what we know as self-induced EMF, and this always opposes any change. Now what is this minus? This minus tells us that it opposes any change in the flow of current, any change in current. So that is my induced EMF. So now with our previous discussion, what we can further say is n phi is nothing but your n into L, that is n, the number of turns n, L is the length of the coil, into mu naught n I into A. So this is actually equal to, if you simplify this, this is actually equal to mu naught n square A L into the current I. So L for us is n into phi, that is number of turns into change in flux divided by the current I, which is nothing but mu naught n square into AL. So if you further simplify, L is nothing but mu r into mu naught into n square AL. Now we have introduced a term mu r. So if, what is this mu r actually signify? So our calculation should have been over at this particular point. So what does this extra mu r signify? This extra mu r signifies, say suppose if you put a magnetic substance inside this solenoid with magnetic susceptibility, then the relative, now you have to understand the relative permeability. For example, the relative permeability changes. So the whole self-inductance of this particular coil changes to mu r times of its initial value, because we have introduced a new magnetic substance who has a relative magnetic permeability mu r. So this is the logic behind this. So now this is all about self-inductance. So if you want to find the amount of work done in this magnetic potential, then we will have in this way. Let's look this in our next slide. So we know the work done with respect to time dt is given by E upon I. So dw upon dt, what is E? E is L I into di upon dt. Now E is minus of L di upon dt into I. So if you take the work done, if I take this value over here, this is equal to, work done is equal to W dw integration of the whole work. Now this is from 0 to I. This is from 0 to I, and that is equal to L into I into di. So from 0 current to the current I, the how much amount of current have we increased? So this work done is actually given by L into I square from 0 to I upon 2. So this is L upon 2 I square. So I square into, sorry, this was L I square. So this is my total expression for work done. W equals to 1 upon 2 into L into I square. So this is my work done for self-inductance.